Greetings and welcome, or welcome back as the case may be. Today I'm going to get back into the habit of doing some science-y posts on Mondays. I decided, basically since I've taken on a new job at my work, I'm working as the operator for the UND Space Studies Observatory. And this next week, we'll be doing with the students some, solar observations. And so a lot of people get confused. How can we look at the sun with our eyes, much less telescopes? Wouldn't that burn your eyes out? And the answer is if you don't have a properly filtered scope, yes, it will. It'll do it so fast, in fact, that you won't even know it's happened. So how do we do it? Well, number one, you've got to do some energy reduction. You are basically going from your eye's aperture is about, in other words, the width of the opening of your eye, your pupil is about 8 millimeters. So you're going from let's see, how many zeros? 0.008 meter to, roughly 0.05 meter or larger. So about 6 to 8 inches. And so you've got to first stop all that energy from getting, or a good portion of that energy from getting down that tube and being focused to a point. So we do that a lot of times by doing things like spraying metal on glass. We use Mylar in a lot of cases, though that's dangerous because if your Mylar isn't thick enough, in other words, if you use the thin stuff like they use in balloons, you're going to burn your eye out. So it's best, even welding glasses are not good enough, mainly because while they damp the visible light, they do not, in a lot of cases, damp the infrared. And your eye does not pick up infrared, so you basically can boil your eye before you know it. This is why you don't use these types of things to look at it. But another thing we like doing with solar observing is looking at particular wavelengths. In other words, very narrow colors. And one of those is a line given off by hydrogen that's been ionized or energized. And that's called the H-alpha line. It is a very, very, very red line, a very, very red color. And we like getting it so that the width of wavelengths around it is very narrow. In fact, we can get it down to about 0.5 angstrom or 0.5 times 10 to the minus 10. So really 9 zeros and a 5 behind the decimal point. So we can get this very well tuned. And so the question becomes, how do we tune it that finely, that carefully? And the answer is usually we use what's called an etalon. Fancy word, it just means 2 plates of semi-silvered, semi-mirrored glass that are put a specific distance apart. And that gap in there basically traps light of any other wavelength except the one we want to let through. It's got to be a certain multiple of wavelengths of the wavelength of the light we want to allow through. Otherwise, the light gets trapped in there, bouncing around between these semi-mirrored surfaces until it's either absorbed or ejected back the way it came. So that's the tools we use to cut down on the amount of light or to focus in. I mean, why might we want to focus in on a particular color? And the answer to that is we can see certain features. In the hydrogen, we can see where all the hydrogen is in the upper atmosphere of the sun. So we can see things like prominences, those arches of plasma that people mistakenly call flares. Those are not flares, though they can be associated with flares. So that's the type of tools we use. And if there's interest, by all means, put comments on it, and I can talk more about any of these topics. But for now, that gives you a brief overview. And we'll let it go. So if you enjoyed the content, give us a like, give us a subscribe, and we'll talk to you next time. So for now, goodbye. Have a good day.